Okay, Igor, and I mean, thanks a lot for this for the introduction and the invitation, of course, to this intelligent conference, active conference. Yeah, so what I want to tell you today is about organization of cognitive self-steering particles. I hope you will see in a minute what I mean by cognitive self-steering. Okay, this direction. Okay, so, okay, I have to get used to it, yeah. Okay, so we know, of course, all that there's a lot of collective motion and swarming in overall length scales here, from microscopic, like these beautiful murmurations of bird flocks, down to the cellular scale, and this is not really a movie, sorry, for the motion of these epithelial cells. Now, what I mean by cognitive particles or self-steering is, you can see here the intelligent motion, right? And that implies what we have heard several times in the conference, is that you sense, the particles sense their environment, they decide on something to do, and they actually act accordingly. Yeah, and I think a nice movie, and I think at least the older people of you have certainly seen this movie about 100 times or more. Right, so this is a neutrophil, a white blood cell, and it chases a bacterium. The bacterium is here, but you can see, right, that it really has to sense the location of the bacterium. It has to redirect its motion in order to follow, and then finally it will catch up. Yeah, so for me, the definition somehow of intelligent behavior is what you see here, right? It's a combination of sensing the environment, processing of the contained information, then some steered activity, and then possibly, if you have many of these particles, some collective motion. Yeah, and just as an illustration for a microbot which can do something like this, but this is just a machine which actually actuated externally. So you just have to see this as a machine which has all the brain and all the actuation and all the vision outside. Yeah, so this is just taken with a camera where you can see this machine and maybe others. And they're also operated externally in the following way. Right, that you, here you have E. coli bacteria, which is caught in these little hollow parts of this structure, and then you can shine light on the on this structure, and if you shine light, then the bacteria are activated, and then you can either shine light on one of them and it turns in one direction, you can shine light on the other side, it turns in the other direction, or you can shine light on both of them and then it moves more or less straight. Yeah? So in this way you can say you see the particle sees nothing, but the camera sees something, and then you direct the motion in such a way that it follows, for example, towards the target. All right. So now, okay, again, I think you know all this, but let me repeat it anyway. Right, so I think there are three main models, three standard models of collective active motion. Yeah, one of them is just active Brownian particles, and yeah, they just move, they collide. And I would say they are active but dumb. Yeah? They do nothing than just run more or less straight and then bump to each other. Then we have the squirmers. That is particles which have flow field on the surface and therefore generate hydrodynamic flows. I would say they're still dumb. They have hydrodynamic interactions, but they are still dumb. And then we have the Witschek particles, where some particle here in the center just looks around and looks what are the other particles are doing, and then adjusts its motion to the motion of the other particles. And I would say this is some kind of intelligence. All right, so that is the outline of what I want to show you. Yeah, so the first thing I want to show you is swarming of some self-steering cognitive active particles. Part one is with visual perception. Part two is visual perception and, in addition, alignment. I will make this very small interlude about steering particles which avoid neighbors, then rather join neighbors. And then this here is mainly about hydrodynamic interactions between these particles. One is noisy pursuit of a moving target by a pursuer. And I will mainly focus on this part with hydrodynamics. And then I will look at the alignment and swarming of many particles So this is something like, with hydrodynamic interaction, this is something like a hydrodynamic Witschek model. All right, so let's start with the first part, particles with visual perception. And here's the model. Yeah, so a particle has a vision cone with some vision angle theta, and it sees particle in the vision cone, and it does not notice any of the other particles. The particles move with constant velocity v0, and there is a torque which redirects the motion direction, and that has a random component, a noise component, and a steering torque. And the steering torque you see here. And I mean, the point I want to make is, so Uij is the connecting vector, unit vector between two particles. So this torque is perpendicular to E, because of course the size, the magnitude of E should not change. And it's 0 if E is already moving in the direction of the target. And so then it's 0, but it's maximum when it's just passing the target on a 90-degree angle. So if the target is here, the particle is moving like this, then it feels a strong torque. But if it's already moving exactly towards the target, no force at all. Yeah, and then so here we have this rotational noise. We have the only particles in the vision cone are considered, and just let me mention that we have to do this non-additivity. So that means here it's divided by the effective number of particles in the vision cone. Yeah. So in this case, therefore, we have interactions which are non-additive, yeah, because of this normalization, and of course they're also non-reciprocal, right? Because this particle sees this red particle, but this red particle has a vision cone over here, and therefore it is not aware of the blue particle. Let me just emphasize that this model was essentially emphasized here in this paper by Barberis and Fernando Peruani already some time ago, and we have looked at it in a little bit more detail. I will explain this in a second. All right, so this is our version of the model. We add an excluded volume interaction, so that whereas Fernando looked at the point particles, you will see that has some consequences, but in many cases also not so important. And then we explore the parameter space in a little bit more detail, right? So the essential parameters are the Peckley number, which is essentially a rescaled velocity, the vision angle, the vision range, the packing fraction. But most importantly, from my point of view, is the maneuverability. That means that is somehow the maximum torque which you can have. So if you look here, right, so this omega v, this is more or less unity, right? So that means you can steer only so much. You cannot somehow go directly toward the target. You can say the target is here. I would like to go there, but you cannot instantaneously change your direction. You have to keep moving until you slowly turn towards the target. And I think that is a very important aspect. Okay. So what phases do we get? I mean, if the vision angle is large, then the particle sees typically several other particles in the vision cone, and it moves towards the place where most other particles are, and this is simply because of this sum. Yeah, so if it steers towards the other particles, but of course several particles are close together, then they contribute all the same contribution here in the sums times their number, whereas there's another one particle somewhere over there, it will hardly contribute. Yeah, so therefore, if the vision angle is large, you see many other particles, you go where most of the other particles are, and you quickly form these big clusters. Yeah? In the other side, if the vision angle is rather small, we often see these worm-like structures, which Fernando had already seen, and in between we see this quote coexistence between the two, but it's not seen, should not be seen as a phase coexistence, but it's one phase. They have both clusters and worms at the same time. Yeah, you can see the worms here, so it's a bit difficult to see, but I hope you can recognize them anyway. Yeah, so sometimes the worm form this little cluster, but then they extend and become elongated, and they move for a while, they collide, and so on. So I think there's already several interesting things in such a warm phase, but we have not really looked at it in any much further detail. Yeah, and of course, this warm phase in a natural system, for example, could be such bird flocks which form this single file motion. Yeah. Another interesting phase, and that didn't really comes only because we have this excluded volume interaction, is this somehow, quote, coexistence between aggregates and worms. Yeah, and you see here that this is not evolving. Yeah, so the worms are sometimes eaten up by the aggregates, but also the aggregates spawn new worms. So therefore, this looks to me like going on forever. At least as long as we can simulate, we never saw any development into one or the other direction. All right, and then as I promised, then we can look at more detail at the parameter dependence. Yeah, so this is the vision angle. Here is large vision angle. Here is small vision angle and Peclet number. Peclet number very small, Peclet number high. This is for some particular maneuverability, and we can also look at for some fixed Peclet number at the dependence on the maneuverability. And I think the main point I want to make is if you look at the stability of the warm phase or this warm aggregate phase, then you see you need high Peclet number, you need high maneuverability, and you also need not too large vision angle. Yeah? Over here at high vision angle, we also always this crystalline phase dominates. If you want to see worms, you have to have a relatively small vision angle. And I think this is all relatively easy to rationalize, right? Why do you need high Peclet number? But I mean, if you want to follow the guy in front of you, you should not somehow have too much rotational diffusion. You should really focus and follow the guy in front. Yeah, the same is true for the vision angle. You should really focus on the guy in front of you and not be distracted by all these other guys which are maybe somewhere in the neighborhood. And the same is true for the good maneuverability, but if the guy in front of you is turning, you should be able to follow the turn. Yeah? All right. Now, now we want to, come on. Now we want to add this alignment interaction, and the reason is, if you think of bird flocks or fish swarms, but it's quite clear that it's not only this vision-induced steering and following, or not only alignment, which makes these swarms, but it has to be the combination of both of them. Yeah? So we need both following and alignment. Yeah, and there were actually some previous studies or suggestions of models. For example, this Boyd model by Reynolds already in 87, and he said essentially this, yeah, if you want to model natural swarms, you have to have alignment and somehow cohesive interactions, and this in a slightly different form was then rediscovered by Ian Cousin from Konstanz, who calls it the behavioral zonal model. And these zones is somehow a short-range repulsion to avoid collisions, then a medium-range alignment, which makes that the swarm is moving in one direction, and then finally this long-range vision-guided cohesion, which keeps the swarm together, right? Otherwise, if two birds are flying off in some direction, they will never find the swarm again. So they have to somehow say, oh, let's look around, where are all these other guys, and then move in this direction. All right, so we take exactly the same model which we had before. Yeah, so this is this model here, the direction of motion guided by the visual torque, and then you just add another torque, which is the alignment torque. And as you see, it has essentially the same form, except that instead of having here this connecting vector between the particles, it's just the orientation of the other particle. And we also take the alignment range is just isotropic. This is this gray area, but otherwise it's normalization, also some maneuverability, and so on. All right, then what do we get in this case? I would say a lot more interesting behavior, right? So first of all, so this is now has of course at least one other parameter, which is this ratio of the maneuverabilities. Yeah, and I think it's clear if the vision I hate it. So if the vision maneuverability dominates, you're going back to the previous model. If the alignment dominates, then of course you are somewhere back to the Witschek model. So we have to be somewhere in between, and this is an interesting ratio. Yeah? So you have more alignment maneuverability than vision maneuverability, and then this is here as a function of Peclet number in this direction and vision angle. Yeah, and then I think it's clear if the vision angle is very small, yeah, you see essentially no structure formation. So you at this intermediate range, the interesting thing is now you get again swarms, but it's not only worms, but it's no longer these linear worms. Therefore, we call them worm-like swarms, and we also get what Ik was showing in the previous talk, maybe with a different underlying physics, but you get this milling structure. Yeah? So all the particles move in a circle, and they keep doing this actually for a very long time. But we see also these very elongated swarms, which again depends then on all these different parameters. Yeah, so here's a movie of this milling, and the other, and this. No. Is this not moving? Ah, yeah, here. So this is this elongated swarm, and I'll show you the trajectory in a bit more detail in a second. As I said, this is the milling. Yeah, so this is the new phases we see in this model where we combine both the following interaction, cohesive interaction and alignment. And then if you look at it in a little bit more detail, then it's interesting that if you look at this kind of motion of such a swarm, yeah, then this is what we call a railway motion, right? Because okay, I hope I will manage at some point this pointer. Okay, yeah, so the green stuff is just the trajectories. And you see that essentially all the swarm just follows what the leader particles are doing. Yeah? But what is interesting, that this motion looks a little bit like a persistent random walk, but I would say it's not, because if you look at it here on a longer length scale, so this is the same time trajectory just over a longer time scale, and you see it really goes persistent random walk-like, but then it makes suddenly these very sharp turns and so on. So I think it's a really interesting motion which really should be analyzed in more detail. Then we can look at what generates actually these kind of elongated worm-like swarms. And I think this is the competition between the two kind of interactions we have, right? So particles want to align, but they also want to point towards the center of mass of what they see in the vision cone. Yeah, so that means particles on the boundary, they are pointed somehow towards the center of the swarm, but they cannot also point directly there because they have this alignment interaction. And this we can look at by considering these two limiting cases. Yeah, so we have a particle at the boundary. The red stuff is supposed to be the swarm. This is at the boundary. So if it has this orientation, then the vision-induced interaction is zero, right? Because the whole vision cone is full. So there is no reason to turn in one or the other direction. So here you have only the alignment interaction. In this limit, the opposite, yeah, so it's perfectly aligned with the swarm, but only half the vision cone is full of particles, therefore it wants to turn towards the swarm. And then we can just interpolate between these two limiting cases, and then we predict that this should be the angle of the particles here at the boundary. Yeah. And you can't see this, of course, from this equation, but if we evaluate this equation and compare it with the numerical results, that's, I would say, the right ballpark. Okay, and then of course there are also natural pictures for these kind of elongated swarms and for the milling. So this here is a herd of sheep, and you see that it forms this elongated structure herd. And also for these bird flocks, you see that it can become very elongated. What's also interesting is the milling here of this reindeer herd. And I mean, if you look closely, then I find this particularly interesting here. These poor guys in the center who really have no idea what to do. They are completely confused. All right. So just as this very quick comment, yeah, we can use the same kind of steering interaction also not to generate a cohesive interaction, but to avoid neighbors. Yeah, and we just have to put a minus sign. Yeah, if you say before we said particle wants to go direct its motion in the direction where the neighbor are. Now we say it goes in the opposite direction. Otherwise the same model. And we also see interesting behavior, and I just show these movies. Yeah, so in this regime, and let's not worry about the parameters, this we call the overcautious regime. So you see particles are essentially not moving because they are so anxious to come close to a neighbor that they immediately turn around. So they go a step forward, they immediately turn back, and there's another neighbor and they immediately turn back and so on. Interesting is this second regime, which we call the wiggling and squirming regime, right? So here the particle really makes some progress, right, by avoiding the neighbors. But what's also interesting is here, if you have a relatively small vision angle, you can actually see structure formation just from avoidance. Yeah, so the particles are moving in these fronts, and we'll see in a second that the fronts become more and more perfect. Yeah, and I think you can understand this motion. Why is it stable to have a front? The reason is the vision cone is small, so if they're all aligned, they don't see each other. But as soon as they turn a bit to one side, they notice, oh, there's actually a neighbor, and they turn back. Yeah, same on the other side. So that stabilizes this front motion. All right, so now this quote second part of my talk is about these hydrodynamic interactions. Yeah, that's fine. So hydrodynamic interactions. I say I will not talk about this case without hydrodynamic interaction in this case. Just another example, right? So this is a sperm cell moving in on the egg. I mean, in this particular case, but this is a side remark, the egg is actually this line, and the reason is there is no egg at all. This is just the chemoattractant, which is in solution in a caged compound, and via light beam you can uncage the chemoattractant, and therefore the chemoattractant is here along the whole line. But you can see this interesting behavior of the sperm. Yeah? So it moves in this helical fashion, and then it notices, oh, I'm kind of beyond the egg, and it makes a rather sharp turn and moves again. Then it notices again going in the wrong direction and so on. So there is actually quite a complicated steering behavior in this case. And even for a stationary target, right? The target is not moving in this case. Okay, so now I want to look at self-steering hydrodynamic interaction, self-steering particles with hydrodynamic interactions. And let's start with just two particles. Yeah? A target and a pursuer. And so of course, we take the Schwärmer model, which I kind of mentioned to you. We have a slip velocity on the surface, which typically is just depending on the polar angle. And then we may have these two principal ways of dipole swimmers, the puller and the pusher. Important is for the hydrodynamic steering, we have actually to break this axial symmetry, right? Because if you just have axial symmetry, you will just swim straight. So what you have to do, you have to somehow push a little bit more on one side than on the other side in order to turn in one direction. Yeah? And we adjust this increased surface velocity in such a way that the orientation axis turns towards this aiming direction. And this is kind of not so essential, but just to make clear. And of course, the target velocity is typically smaller than the pursuer velocity, because otherwise we are in a boring situation that the target just runs away and the pursuer will never catch up. Yeah, so for those of you who have not seen this, and if you look at pushers, there's this flow field that the pusher pushes the fluid backwards on the back. This is the propeller. But there's this load, the passive head, and that pushes the fluid forward. Therefore, you see this flow field flow towards the front, at the front, flow to the back, and the sidewise inflow. And that is important, for example, if you take two pushers, then they actually hydrodynamically attract each other. All right, so now what do we see? Yeah, so a first example is we have two pushers. Both the target and the pursuer is a pusher, and as I said, the pursuer is faster. And now you see what happens. The pursuer can not catch up with the target. Yeah, so it always keeps, for a long time, it keeps at a more or less constant distance. Yeah, and the reason is this flow field. Yeah, because the target pushes fluid back and the pursuer pushes fluid forward, so they have this repulsive hydrodynamic interaction between them. Yeah, and this is actually an effect which also is important in marine life, so that if small fishes tries to catch food, then they have the same problem. They move towards the food, but the fluid flow which they generate actually pushes the food away, and that is called a hydrodynamic starvation. Okay, the second example I want to show is now we have not a following interaction, but an alignment interaction. Yeah, so the pursuer tries to align with the motion direction of the target. Yeah? And then this situation that you have two particles close by with the same alignment is actually unstable. And the reason is that you have a torque. And I think we heard this in some of the previous talks, right? So think of, say, this situation, right? Then this particle generates a flow field like this, which you saw on the previous transparency, and that generates a rotation in the target. So the target moves away, and if the pursuer just moves straight ahead, then they lose contact. Yeah, so you need, and the the pusher-pusher attraction hydrodynamic is not enough to compensate for this. So what you need is in addition a speed adaptation. Yeah, so that means if this particle, say, is lagging a little bit behind, and it has to lag behind because you see that it has to travel a longer trajectory, it speeds up a bit. Yeah, and then if it somehow overshoots a bit maybe, then it slows down again. So, but that you really need the adaptation. It's not enough to say that the pursuer is a bit faster, but because that just means they separate even more easily. Yeah, and then you can see these nice trajectories here. So I would say this is maybe even better than a dance of Volvox. This is a real dance. Yeah, so they do this somehow circular motion for a while, and then maybe one of them by fluctuations gets a bit ahead or so, and then you see these sharp turns and so on. All right, so last three transparencies is now about this hydrodynamic Witschek model. Again, this is not discovered by us, but it has been shown long time ago. With hydrodynamic interaction, these aligned phases or polar phases are unstable. Yeah, so therefore, the phase in the Witschek model where you say everything is polarly aligned does not exist if you have hydrodynamic interactions. And the question is, what happens then? Yeah, what replaces the motion of the polar aligned phase? Yeah, so we do large-scale hydrodynamic simulations, and this is really large-scale, as you can see here. So in this simulation box, we have typically 10 to the 5 to the 10 to the 6 squirmers. Right? This is for pushers in this case, and we have a self-steering to align the propulsion direction with the neighbors, so therefore Witschek. Yeah? And then what you see, and that you see here, right? That is hydrodynamic active turbulence. Yeah? So pushers that have this self-steering alignment show active turbulence. Yeah, we can quantify this a bit. Let me not go into the detail. Yeah, but what you see here is that the density, this is a local density distribution. This is the average density, and you see everything is more or less at the average density. So this is a pretty homogeneous spatial distribution. And then we can also calculate the kinetic energy spectrum. And then we see this typically characteristic power law decay as a function of the wave vector k with some power. What's interesting is that if you have very little steering, yeah, so example here 32, you see hardly anything. So you really need a strong steering in order to get a pronounced active turbulence. And what's also interesting, if you look at the peak value here, that this peak value is 20 times this V0. So that means the particles in this active turbulence move actually faster than the particles would swim themselves. And that is actually also, you can also see in the mean square displacement, you just see that this ballistic part of the mean square displacement just shifted up. So particles really move faster in these whatever large vortices. Now, if we do the same thing for pullers, then we see a completely different behavior. Yeah, and that we just heard the movie. Yeah, you see a very inhomogeneous, heterogeneous structure now. Yeah, you see the formation of clusters, vortices, and jets. And, yeah, and if you look at this cluster formation, if you look at this cluster formation, right, then you see, so this is somehow a kind of time sequence. Yeah, first you see the clusters are forming, then they are lining because of alignment interaction. That generates a large fluid jet, and that is somehow a fluid vortex, which you can vaguely recognize here, and that then actually rips the cluster apart again. So therefore you have this constant sequence of cluster formation, vortex, and destruction of the cluster, and then formation of a new cluster and so on. All right, I think I have extended my time. I don't think we have to, I mean, you can take a look at it. Thanks for your attention.